everyone. It is a great honor to be here, and also a great honor to be the first speaker of the workshop. The climate informatics community is very close to my heart, and I came here about 4 or 5 years ago when I was a PhD student. Now, I came here as a speaker, but I do see a lot of familiar faces and as well as new faces, so it's good to be back. Thank you very much for the program committee and, Jacob especially, and, Nico and Dan to organize this workshop. So I was asked to talk about deep learning. I don't consider myself as a deep learning person. I work a lot about learning from large-scale spatial temporal data, and one of the methods we tried is deep learning. So today, I'm just going to share with you some experience through our research in terms of, what are the challenges and what are opportunities in applying deep learning to spatial temporal data. So one of the motivations for my research is sustainability. There are several applications I'm putting on the slides here. Right now, if you look at transportation, research have shown that $124 billion per year was actually wasted due to traffic congestion. And we still don't have a very efficient way of predicting traffic and planning for optimal routes. The second application is in the energy industry. Scientists have found out that actually 61% of the generated energy is wasted due to the lack of efficient and effective data analytic pipeline. The third application is in the climate science, and $1.5 trillion were basically destroyed due to natural disasters, and we still don't have a way to precisely forecast those natural disasters and fire alerts. Now, if you look at all those different domains, one common pattern you can see is that the data that is generated from those domains contain very rich spatial and temporal information. So if we can extract knowledge from this massive amount of spatial temporal data, we will be able to make progress towards addressing the sustainability issues of our society. So the overarching goal of my research, as I'm starting a faculty job, is to cast a lot of the spatial temporal problems into learning problems. Basically, we take the data that was generated in these different domains and then develop machine learning algorithms for this data so that we can solve problems such as time series forecasting, dependency modeling, change point detection, and etc. If we can solve those problems, then we will be able towards making real-time sequential decisions, right? And then we can make better control for traffic, and it enable us to do dynamic dynamic pricing, and many other tasks. So, as opposed to many other kind of data types in machine learning, such as images or language, spatial temporal data has its unique challenges. One of those challenges is spatial temporal correlation, right? So in machine learning, people usually assume the data points are independently identically distributed. Whereas for spatial temporal data, there's very strong spatial autocorrelation and temporal autocorrelation, which leads to computational challenges. The second challenge is nonlinear dynamics. So one example for nonlinear dynamics is traffic. So what I mean by nonlinear dynamics is, the data that is presented here that is generated from this dynamics cannot be simply captured by linear models. The consequence for nonlinear dynamics is that it can be chaotic. It can also be periodic. Therefore, very, very difficult to make predictions on. The third challenge is high dimensionality. So when I talk about high dimensionality, it's not only about the dimensionality of variables or features, it's also about the dimensionality of the time and the space. When we're working with spatiotemporal data, the dimensionality of a time can be hundreds of thousands. The number of locations we are looking at can be up to millions. The curse of dimensionality means it can lead to overfitting. On top of that, it can also make it very unstable in terms of numerical computations. So, with all those challenges, we have been working on this domain and trying to address some of the challenges from many different methods. As far as I know, a lot of the experts here, they're like VPing, like experts in spatiotemporal data. So there are a lot of different methods for addressing the challenges, and today I'm just going to talk about one of them, deep learning. Well, the reason for that is we heard a lot of promises for deep learning, right? So the first idea came into my mind is, let's just try it and see how it works. So people say, well, deep learning allows us to automatically extract features. It doesn't require domain knowledge, which is cheap to obtain, right? People in the literature, they tend to manually craft features. For example, we can take some time series and compute Fourier transformation and take the frequency and the magnitude as features for this time series. But the downside of that is it's very computational expensive, right? That's one of the promises for deep learning. The second promise for deep learning, it gives us expressive models. So as I mentioned, spatiotemporal data has very high correlation not only on time and space, right? So if we only take simple models, it might not be enough to capture this complex correlation. And deep learning models, because of the layers neural nets and nonlinear activation functions, we actually can, to a certain extent, capture the long-term and long-range correlation and model the nonlinear dynamics. The third promise is scalability. So there's this plot I took from the internet. I would take this plot with a grain of salt. It compares with a deep learning with many traditional learning methods. And it said, okay, if we have more data, then the performance of deep learning will get better. Where this rate is higher than traditional methods. It's true for certain applications. So we're scientists here. We have critical views of everything. And I take it with a grain of salt. So the promise of deep learning is that we can take in all those massive data sets and hopefully address some complex problems, right? Probably you have seen like machine translation, object recognition. Those tests are rather complex. So we have seen some success of deep learning applying to those tests. So today, I'm just going to talk about two of the work that we tried, and we have seen some promising results. This work is published in some iClear, one of the deep learning venues. But most important, I just want to share with you some experience and get your feedback. So the first project I'm going to talk about is spatiotemporal forecasting. So spatiotemporal forecasting is a very classic problem in spatiotemporal analysis. I know climate scientists don't like to talk about forecasting. Usually they use projection. If you don't like forecasting, please bear with me. But I welcome critics for the work. So forecasting takes some input from p different locations, denoted as xt minus 1 up to x1 to xp, right? And we take k length of history. People call it autocorrelation window. So this is the assumption for the length of the autocorrelation, just as a data. So we take this history and trying to make predictions for the future. Then here we want to perform predictions for a longer future. instead of predicting for the next time point, we want to predicting up to up to h time point, right? That's the forecasting horizon. And we're looking at spatial temporal forecasting. So we can construct a graph based on the spatial correlation, right? So then we have 4 locations here. We can construct a graph that connects them together. And the problem of the question of spatial temporal forecasting is basically looking at the signals generated from different locations and take the history, predict the future. Right? That's spatial temporal forecasting. There are a lot of applications for spatial temporal forecasting. For example, we can model the human body as a graph. Then we take the sensory data, such as your Fitbit, right? Then we can recognize activities from your sensory data. And this is also a spatial temporal forecasting problem. We can deal with Internet of Things, right? One of the collaborators I had, he's trying to use spatial temporal forecasting to predict whether this building is stable or not by taking the sensors, installed in different corners of the building, right? Of course, it's useful in climate science. And I'm just going to use one simple example, traffic forecasting, to illustrate the point. But you can think of other data types, and I don't think the methodology is limited to traffic forecasting. So spatial temporal forecasting, takes some history, right, and build a graph, and generate a sequence of future graphs. So let's look at an example for traffic. Now, what is so hard about traffic forecasting? Well, we're looking at 3 sensors together, right? Row 1, row 2, and row 3. All those 3 sensors are very close to each other. So in terms of Euclidean distance, they're pretty much the same. But let's look at the speed over time visualization of the data. So the blue line and the red line, they're similar, right, in terms of patterns. The yellow line, not so much, right? Why is that? Oh, we know, by common sense, traffic from uptown or from downtown, they're very different. Those people commute, right? And mathematically, it just means the data is non-Euclidean. A second challenge of traffic forecasting is nonlinear, right? So we look at the time series here. If we do linear interpolation, the error will be big, right? And it's non-stationary. So those 2 combined challenges make this problem hard, right? Okay, let's try the first version of deep neural net, which is recurrent neural net. Probably many of you are familiar with it. The definition of recurrent neural nets is a generalization of Markov models, right? So if we have some input states s at time t, and we have some hidden states h at time t, and outputs y at time t. RNN defines the transition function as the hidden state at time t is basically a sigma function over some linear combinations of inputs and hidden states from the past timestamp, right? And then the sigma function, casts the value into 0, 1, so which give you the probability. And the sigma function is usually known as activation function. Then the parameters here, theta, they are the weights of the neural net. So you can learn the values of this theta through training of neural nets, right? And the output yt is defined as, again, a linear relationship of some weights, some parameter theta, and the hidden state at the current timestamp. Now we include a bias term here, right? And this is just one equation that represents the transition from time t minus 1 to time t. And RNN basically unfolds this equation to infinite number of times. So we have this infinite loop, then when you unfold it, it becomes infinite, right? And I want to make note that the hidden states here, they're deterministic. Just wanted to keep in mind. RNN famous in deep learning, but it has an issue called vanishing gradient. Because when we unfold the RNN into infinite number of timestamps, and when we train the neural nets with gradient descent, sometimes the gradient becomes 0, so that the neural net don't remember the history anymore. So that people have found that using RNN can only memorize sequence up to 50 timestamps. People have thought ways to address it. One of them is to use memory. And here we go. We have a gated recurrent unit, which is a more advanced version of RNN. And the key contribution of GRU, which is not mine, is to include this memory unit here, so that you have a logical switch here where you decide whether I throw away the history or I kind of borrow information from history, right? And it's a way to address vanishing gradient problem. People probably here, you guys are familiar with LSTM, right? Which was designed with similar motivation, and GRU is a simplified version of LSTM, which is easier to train. Here's the equation. You don't have to remember it. Basically, you have this switch R, and then the switch R is trained very similar to the hidden state transition, where you have the sigmoid function on top of some linear combinations of inputs and hidden states. And then because of this R, it gives you a switch, right? Sometimes you borrow information from the history. Sometimes you just forget what happened. Okay, then let's talk about traffic forecasting. As I mentioned, one of the challenges is to address the spatial dependency. And the spatial dependency of traffic forecasting is non-Euclidean, right? Then how can we model non-Euclidean spatial patterns? The way we deal with it is to think of traffic flow as a diffusion process. So what is diffusion process? If you pour a liquid onto a surface, you watch the water diffuse on the surface. That's a diffusion process, right? And we basically define a specific operation called graph diffusion convolution that can encode the spatial dependency. And then we combine this graph diffusion operation into the neural nets to capture spatial dependency. That's our contribution. And specifically, given this road network graph, right? It can be also your climate stations. We know the distance between two nodes, right? Two locations. So we can construct, we can represent this graph using adjacency matrix. And the element of this adjacency matrix, Wij, is the inverse of distance. Here, distance net is a network distance. So this is something very particular to a transportation community, where they define the distance between two nodes as according to the travel time. So you have the directional information encoded there. And with this adjacency matrix, we have in-degree matrix, which is a summation over all the rows. And then we have the out-degree matrix, which is summation over all the columns. Right? So the diffusion process basically can be think of as like we have a distribution over a flow, a traffic flow. Right? Imagine cars, concentrate at different locations of the road network. So the diffusion process models the dynamics as several steps of propagation of flows over this network. And basically, we can see that if we have a diffusion filter that's centered around here, we can write this diffusion filter as a linear combination of multi-step diffusions, right? So if we have first step, then it diffuses into the first neighbors, and then we can do the same for the second and third neighbors as well. The reason we use it is also has a very nice theoretical results from 2016, which states the stationary distribution of this diffusion process is actually can be written out as a weighted combination of infinite random walk. Right? So imagine like we let the cars to random walk for a little bit, but it's a proxy, it's approximation. And this basically casts a continuous distribution as something that is discrete. Right? Then we can compute. And here is some weighted combination, and k is number of diffusion timestamps. So if we raise it to the kth power, that means we let the diffusion process execute for k discrete timestamps. And here, the inverse of the out degree matrix times adjacency matrix, this is called random walk matrix in graph theory. So with this definition of diffusion process, we can define the diffusion convolutional kernel. Right? So this kernel enables us to transform the inputs that are originally distributed as a graph into something that neural nets can process. And through this processing, we're not losing spatial information, especially the directional information in the traffic flow. And the nice thing about this diffusion convolutional kernel is that it is relatively cheap to compute. So the time complexity of this kernel is basically to the order of number of edges, as opposed to if you compute the adjacency matrix, basically the quadratic square of the number of vertices, right? And second of all, the diffusion convolutional kernel is quite expressive. So it basically defines an operation on a directed graph. You can plug this into any type of neural architecture, your favorite architecture. And here we just use GRU as an example. And formally, the diffusion convolutional kernel basically performs a convolutional operation between the input x and some function, which is basically your features. Right? And then this is defined as a weighted combination of k-step diffusion. We have some parameters theta, one which is out degree, so it's like out diffusion process, the other direction. Then we have similar definition for the in degree random walk, right? So we have this two-directional diffusion process, and then once we multiply this term on top of the input, we transform the graphs into something that can be processed by neural nets. So that's about spatial dependency and how we take care of that. Then how about the temporal dependency? So because we want to forecast or make projections for future, right? We want to make predictions for a rather long future. Well, we borrowed an idea from language, which is a sequence-to-sequence architecture. So the sequence-to-sequence architecture basically composed of two parts. The first is an encoder, which encodes your history into some hidden states. Right? These hidden states can be the autocorrelations, but because neural nets are very difficult to interpret, I don't have a mathematical definition of what is actually encoded from the encoder. And then the second part of the sequence-to-sequence architecture is the decoder, where you take the hidden states, the hidden representations learned by the neural net, into something that is that are your outputs, right? And this is your history, and this is your future. And the length of the decoder represents the prediction window, the forecasting horizon. And seq-to-seq model has been successfully applied to many kind of sequence prediction tasks, such as machine translation or video prediction, etc. So with these two components, spatial dependency with diffusion convolutional kernel and temporal dependency with sequence-to-sequence architecture, we put them together, which becomes our model, right? So how do you compute it? Imagine that for each unit, we're using GRU, right? Getty recurrent unit, and we have the equation here where there's some memory unit that is computed as an activation function on top of a linear combination of parameters, matrix multiply the input x and the hidden state h, right? And to compute the graph convolutional, diffusion convolutional, we only need to do one change, which basically replace this matrix multiplication with graph convolution, as we defined before, right? And you can do the same for all the other transition functions that we have defined before, replacing the matrix multiplication with graph convolution. And with that, this is the architecture that we are using for the spatiotemporal forecasting problem. Basically, we're given a sequence of graphs, right? The structure of the graph does not change, where the signals coming out of the nodes of the graph changes over time. Right? Think of the traffic forecasting example or some sort of climate prediction example. And we embed each of the cell, right, the modified gated recurrent unit, into both the encoder and the decoder architecture, right, in a sequence kind of form. And we perform the diffusion convolution recurrent in each of the layers, and then it gives us predictions for the future graphs. Right? That's our forecasted value. We used, so that's seek-to-seek, right, with DC GRU, diffusion convolutional GRU. We also use the schedule sampling. So basically, the motivation for using schedule sampling technique is that when we make predictions, right, so the purple color are the model predictions. And during training, sometimes you also have observation. You have your training data, right? Your observed sequences, right? And because the error propagation issue means if you only take the forecast as ground truth and just let it propagate over time, and the error will become huge. So during training, the model has no way to learn about this error propagation. So schedule sampling is a very simple technique, which basically says, well, sometimes you take it's more like a heuristic. Sometimes you take the ground truth, and sometimes you take the model prediction, right? So you just flip a coin, where then in the output of the decoder, you sometimes take the model prediction, and you sometimes take the observation. And there's basically you can increase this mixture rate. So that's what people call schedule, right? Sampling schedule. So you can say, well, in the beginning where my model is very wrong, and I take more observations. As I train for more iterations, my model hopefully becomes better, so I can take more predictions, right? So that you have this sampling rate over number of iterations kind of curve, right? So then let's look at some results. This is tested on 2 traffic sensor data sets, one from LA, one from the Bay Area. I was original from LA, so we took the data from the LA Metro, and we tried a bunch of things, made it work. Now LA Metro is implementing the system. So we take the bunch of sensors, right? Take some about 6.5 million observations. We want to perform traffic forecasting. So the state of art of traffic forecasting is about 15 minutes accurately. With this model, we're able to push the limit to 1 hour. And if you look at the LA predictions, right, we compare with the DCR, and the orange curve is our model. This is showing the mean absolute error versus different forecasting horizons. And the orange line is our model. We compared with historical average, which actually Google Map uses, by the way. ARIMA is a classic time series model. VAR model is a multivariate version of that. SVR is a kernel version of that. Support vector regression. We compare with a bunch of traditional sequence-to-sequence architectures. For example, the one with dense nets or the one with LSTM. We can see that our prediction is quite accurate compared to the other baselines. And this is mile per hour. So for 1 hour ahead forecasting, our error is around 3.5 miles per hour. And we did the same experiments for the Bay Area traffic. So we see similar patterns, right? As we forecast longer, the error becomes larger, which is understandable. And our method is more accurate compared to the other baselines. And then the one interesting thing is you can see that for 1 hour ahead prediction, the error is around 2 miles per hour. Right? It's actually better than the traffic in LA. if you have ever been to LA or, Bay Area, then you probably know. In Bay Area, there's only one highway, so it's very regular, right? Well, in LA, it's a spider net, and it's rather difficult to forecast. So let's look at some predictions. So this plot is the visualization of the filters that we learned, right? We construct this diffusion convolutional kernel, and we have some weighted combination of different steps of diffusion. Right? So then this visualizes the graph net after converted into multi-step diffusion. What are the hubs, the diffusion center that are learned from this neural net? If you've ever been to LA, so this part is the crossing between 405, Highway 405, and close to the Hollywood. And this part is a little bit further to the east of Beverly Hills. The other part is downtown. Those three hubs are identified by the model as the diffusion center of the traffic flow. And then we look at the predictions of our model compared to traditional sequence-to-sequence with LSTM. This is mainly to show that incorporating the spatial dependency or using the graph kernel, there's some benefit to it. So the blue curve is the ground truth traffic signal, right? This is a mile per hour over number of time. And the green line here is the prediction from the baseline, and the orange line is the prediction from our model. This sort of gives you a sense of why our model is doing a little better than the baseline, because when there's a traffic dip, right, when there's a traffic accident, then our model, the orange line, can align better with the ground truth, which is the blue curve here, right? That's the prediction realization. So that's the first work for spatial temporal forecasting. And this work is about, well, okay, we take care of the spatial and temporal dependency to a certain extent. But how about nonlinear and high-order dynamics, right? So we can do 1 hour forecasting, but how about even longer? And that kind of motivated this work. Some people who know me probably are familiar with some work we did before about tensors, right? So tensor is a high-order model. They can model nonlinear structure. And in this work, we basically use tensor as a tool and combined with recurrent neural nets to handle nonlinearity. So difficulties in nonlinear environments. As I mentioned before, if we have the time series, this is the temperature over years. This is the traffic speed over hour, and the patterns are very nonlinear, right? And then you can see a lot of drops here. They're missing values. It's pretty messy. And the long-term dependency basically means, well, the traffic or the climate can not only depend on the patterns from most recent weeks, it can up to years or decades. So this is long-term dependency here. And how the correlation I talked about before. So if we want to make forecasting for this kind of problem, and we let it run for really long time horizon, the error propagation will be a problem, right? So long-term forecasting. Mathematically, you can write the problem of long-term forecasting as follows, right? So suppose we're given a system, and the state at the current timestamp is denoted as xt. And imagine the system has some parameters that we don't know. If we have a perfect model, then the system can be written out as a sequence of differential equations, right? So this captures the relationship of the state, the acceleration of the velocity of the state, and the acceleration of the state. If the model is perfect, then we can accurately describe this dynamical system without error. But that's not true, because in reality, most of the models are wrong. And in long-term forecasting, we want to learn basically a function that kind of adjusts this imperfectness of the model. We take some data that is generated from the system which can contain error or unobserved states. Then we try to learn this model F purely based on data so that we can make predictions for the future, right, xt minus 1 from the y0t to, the future from the history, x0 to the blue curve to the red curve, right? And we talked about RNNs. So RNN is basically a first-order Markov model, right? You can think of, the transition function only takes the hidden states from the previous timestamp, t minus 1, right? And then map it to the hidden state at the next timestamp. And the output will be some function g over the hidden state at the current timestamp. And this is first-order Markov model. And I mentioned before, this model suffers from gradient vanishing problem and has very limited capacity to capture long-term dependency. So people have actually thought about, okay, what if we actually include more terms in this transition function? So imagine generalizing the first-order Markov model to high-order Markov model, right? So instead of taking the hidden states from the past timestamp only, we try to take the hidden states from a rather long-term horizon. And this one takes the hidden states from up to L history, right? And that's L-order Markov. And another thing is that right now, this transition function is some linear combination of weights and the hidden states, right? So this only captures the linear relationship in terms of interactions between hidden states and the neural net weights, right? So the second idea we had is, well, can we actually include high-order terms, like polynomial interactions, in this hidden transition? What we can do is that we can construct an augmented hidden states, which basically include the history up to L length. And then we can construct a tensor outer product of all those hidden states, right? And this tensor product of all the augmented hidden states basically is all the polynomial expansions. Can be ht minus 1, ht minus 1 times ht minus 2, right? You can also raise it to up to p power. So it's a pretty straightforward way to construct high-order terms in non-Markovian models, right? We have L-order Markov, and we have polynomial interactions. And then once we include this power, tensor product of augmented states, we can assign a neural net weight to train it, right? And the dimension of this weight tensor is basically number of inputs times the length to the power of p, the time length up to power of p. Right? Then the issue is that it's very difficult to compute. Before I talk about how we address this problem, let's recall the first-order RNN with seq-to-seq model, right? So seq-to-seq model basically takes an encoder and decoder, right? 2 parts. And the encoder takes the inputs from history and then runs through the hidden states up to t timestamps. After that, use this hidden transit representation into the decoder, and the decoder generates the outputs for the future, right? And the model that we proposed, high-order tensor RNN, is basically incorporating 2 types of high-order terms. This is high-order tensor RNN, short for hot RNN, hot RNN. And hot LSTM is basically, hot RNN with LSTM cells. This encoder, so what's happening is like, okay, we take some hidden states, right? Instead of taking only one hidden state, we take a bunch of them. And then we construct an augmented hidden state, right? This augmented hidden state S is a longer history. And then we pass, we construct the tensor product of this augmented hidden state through this tensor unit, the red unit, which I will talk about after this slide, right? And then you propagate the hidden representations to the decoder, and the decoder does the same thing. And this generates the predictions for the future. So what is this red unit, right? As I mentioned before, the issue of incorporating high-order terms is the number of parameters that we have to learn becomes exponential, which make it very difficult to train a deep recurrent neural net, right? And we basically encode the tensor decomposition into the neural net. And specifically, we used tensor train decomposition. So tensor train decomposition, compared to a lot of the other tensor architectures, such as Tucker decomposition or CP decomposition, is dimension-free, meaning the number of parameters in the tensor train model is only linear to the dimension of the tensor. That's one of the benefits of using tensor train. And we encode this tensor train decomposition into this recurrent cell. So once we construct, this powers of the augmented states, right, denoted as this tensor, we can reduce the dimensionality of the parameters through tensor train decomposition. And now the number of parameters of our neural net becomes much smaller, right? And another nice thing about hot RNN is that we can bound the number of hidden units we need to use in order to learn a particular transition function. So we have theoretical guarantees for our model. And basically, if we're given a state transition function, f, we need some assumption on this state transition f. So it has to be Holder continuous, right, up to kth order differentiable. And then we can bound the this is basically the estimation error. So the estimation error is trying to say how powerful this neural net, this tensor RNN neural net is, with respect to the number of units, hidden units, and the properties of the target function that you want to approximate, right? Because we all know like neural nets are universal function approximators, but how close like the approximation is stated by this theorem. And it basically said, well, the approximation error is upper bounded by something related to the size of the state, D, and inverse proportional to the tensor train rank, R, and the order of our polynomial, P. Right? There are three terms. So it basically means if we have more hidden units, then we can approximate better. And similarly, if we have higher rank of the tensor, the approximation is better. And with this P term, it basically means tensor RN is better, or like have more approximation power than plain RN, where P equals to 1, right? And the take-home message for this theorem is that the number of weights dictated by its regularity, which is the second term. This first term is dominant. The expressiveness is driven by the selection of rank, R, and the polynomial term, P, right? And if we increase the regularity, which is basically denoted by the constant here, like the C of K is the regularity of the function. So if we have better function, the better function is easier, approximation is better. If you just want to approximate a linear line, it's pretty straightforward. That's kind of the take-home message for this theorem. So if we look at the forecasting for the sensor data from traffic and this is for the traffic data, right? Then we can actually do better for up to, this is 18 hours ahead. So we did improve on the forecasting horizon. And we compare with, traditional LSTM, MLSTM, which is the high order term without the polynomial, right? We just concatenate more hidden states. And our model, which is hot LSTM. So this is prediction error normalized. Root mean square is normalized data, by the way, over the number of hours. I want to note that this model does not include a spatial dependency yet. This model just focused on the temporal, right? So we want to address the high order forecasting problem. So that's why we didn't compare with, the giddy recurrent diffusion convolutional kernel that I mentioned before. If we look at some predictions, right? So this is the traffic flow, right? And this is the red line is our prediction, and the yellow line is LSTM. So we can capture this dips or like not irregularity better than the method that we used as baseline. When we did similar things for the client temperature sequence, I'm not super satisfied with these results. But overall, like you can see the hot LSTM basically in terms of number of days predict over the RMSE. So our model is more stable in terms of long-term forecasting. Right? So the error propagation is mitigated in certain way, to a certain extent compared to the traditional deep learning architecture like LST, sequence-to-sequence LSTM, or our other baselines. And the predictions, I wouldn't say they look great. It's pretty difficult. So the red line is here, but it's completely forget about scarcity of the data. So I'm not particularly proud of this result, but I want to show, this is what we tried, right? This is what results look like. And we, one of the motivation for entire project is basically to learn nonlinear dynamics, right? Using tensor structure. So that one example is chaotic problem, and this is a Lorentz system, right? So we want to take a purely data-driven approach where we're given, say, some samples from this Lorentz trajectory, and we want to make predictions for the future to capture the contraction effect, the attractor effect. That's the original motivation for this project. And we take some samples, which are denoted as the red dots here, and we generate the sequence and try to make predictions for the future. Lorentz attractor is famous for, being difficult, chaotic, and a very small perturbation can lead to different behavior. So let's look at the predictions. The red dots are the ground truths, right? The samples that we see, and the blue curve is our prediction. So we basically just take the predictions and interpolate them. This is for 20 times ahead. This looks okay, right? We can do this. How about later? And we want to do, this is 40 times ahead. So once we do 40 times ahead with predictions, you see there's a little gap here, right? Between the ground truth, the red dot, and the prediction, the blue line. And you see there's the error start to appear after we forecast for 40 times ahead. How about later? Completely goes off the track, right? Because of the nature of chaotic system, a little error here will lead to catastrophic phenomenon. One of the students who have been working with me, he spent some time which improves the 40 times ahead to 60. That's kind of state of art for this problem. We're still thinking of ways how to deal with it, so I'll just leave it as an open problem. So this is some shameless self-promotion for my research. And my research focus on spatial-temporal data, right? Learn dynamics from spatial-temporal data. And one of the examples is basketball data, right? So in basketball, we take the tracking data from different basketball players. So they move around, it's spatial. They change behavior, temporal. Right? We look at the behavior of the tracking data and trying to make predictions for the strategy. Right? So the goal here is to build a neural simulator that can help train professional coaches to design better team strategy. So we designed a multi-resolution RNN with adversarial training. You don't have to know the details, but the goal here is to imitate the basketball behavior, the basketball player's behavior, right, at different resolution. Here are the results, right? Suppose, so these are 5 players, right? The black dots are the starting point. So this multi-resolution model goes as follows. Well, we're given, suppose we give the model the starting point and the end point of this trajectory. And we want the model to learn at different temporal a different spatial resolution, the interpolation strategy, right? Figure out the tracks between the starting point and the end point. And from 16 to 1 basically means the resolution granularity. Originally, 16 means like we only interpret in the between, one dot in between, right? Given the starting point and end point. And then it goes on. Suppose we know the middle point, then what is the quarter point? And by the way, this model is trained completely unsupervised, which is different from the sequence-to-sequence architecture I mentioned before, which is supervised. This is unsupervised. Then we want to learn a model that essentially gives us a very fine-grained trajectory that is comparable to the expert data, which is generated by the professional basketball players. You can see that the blue, this blue circle, the trajectory is here, and in this red circle, the expert trajectory. So the computer generates something that is very similar to human data. Usually it's fun to do Turing tests, so because of time constraints, and I just passed this time. So I would like to do Turing tests, and which you really have a lot of fun. That's one. And the other thing is, learn the dynamics from control, right? Learning inverse dynamics. And so this is a drone, the UAV, right? It is divided by Newtonian dynamics. Usually, if you want to just fly the drone at the normal condition, it's pretty easy. But when you fly the drone close to the ground, because of the chaotic aerodynamics, right, most people know, there's something called ground effect, where the drone cannot land on the ground, like as close as possible. It's called ground effect. So what we did is just to use deep learning, to learn the inverse dynamics by taking the observational data from the drones. So we combine the control model and the deep learning model, so that this is basically the landing area along the vertical z area, the vertical line, and this is the time, right? So you can just imagine the drone flying, vertically land on the ground, right? So the closer, so the dashed line here is target, which you want to close to the ground, right? And the red line here is the traditional controller without learning, and the blue line is our model, control plus deep learning. Then we can see that, final error, we actually can compensate the ground effect. There's some research and vignettes that I've done to learn dynamics with deep learning. But as I mentioned before, deep learning is not the golden standard for learning spatial-temporal data. There are tons of pitfalls of deep learning. Some examples I'm showing here. Nonlinear dynamics is hard. This is another project I was involved with. Basically, we want to take, some Navier-Stokes sequencing examples, that simulate the fluid dynamics, right? The smoke, for example, and trying to make predictions for future smoke propagation. So we have some. This is just example data. So we have some starting point here. There are two starting points of the smoke, right? And the smoke propagates. Then we want to forecast for this kind of data. So I spend a lot of time trying to come up with the architecture that can make forecasts for this kind of data, but I failed. That just shows nonlinear dynamics is hard, right? As I mentioned, even for the simple Lorentz example, we cannot forecast up to 60 time steps ahead. Of course, it depends on your, fine granularity of the discretization granularity of your dynamics, but nonlinear dynamics is hard. Probabilistic inference challenging. The plots I've showed you, we have some predictions that kind of capture the mean, right? But where is the stochasticity? There's no stochasticity. Like the data itself have a lot of zigzags, right? Similar for the traffic data. And then the traffic data have a lot of stochasticity. But the model, because the hidden states, as I mentioned before, they are deterministic. So it doesn't allow us to perform probabilistic inference, which is very important for a lot of scientific applications. Right? So that's something that we're working on right now. Another pitfall is deep learning. What is notorious is sensitive to input perturbation. Right? We have some panda, we add some noise, and just predict as like given with 99% accuracy. This is an example from Ian's paper called adversarial examples. Right? So we haven't really seen similar behavior for spatial temporal data, but people have shown it for videos. The main issue is high dimensionality, so it's very sensitive to input perturbation. The last thing I want to mention is like physical interpretation. Right? So in climate science, we build a lot of physical models. And we know the meaning of those parameters, and we have a really nice physical interpolation. For example, this Navier-Stokes equation. If we look at this equation, we know that the law of energy conservation is implicit in this equation, right? But then when I try to use deep learning to make predictions for the smoke, it was challenging for me to incorporate this law of energy conservation into my model. Right? It's kind of difficult. So the current deep learning method, they don't have any physical interpolation. That's hard. No, those are some pitfalls of deep learning. Just as a take-home message for my research so far, I'm starting this group in Northeastern. We're trying to work this out. We're focused on this. But if you have any questions or you want to discuss some fun problems in spatial temporal data, please reach out to me. My email is roseu@northeastern.edu. Thank you very much.